Hello, my name is Dr. Garrett Struckoff, and today we are going to be talking about the periodic table of the elements. We will talk about the parts of an atom, elements themselves, the periodic table and ways to use it, some examples, and some practice problems for you to work on your own. The parts of an atom, which you learned about in chemistry, are broadly broken down into the nucleus and the electron field. The nucleus is composed of the protons, which are positively charged subatomic particles, and neutrons, which are uncharged particles that have a similar mass to a proton. In the electron field, we have electrons, which are negatively charged particles outside of the nucleus, much smaller and lighter than protons and neutrons. We worry about the valence electrons. If electrons have the proper number of electrons in their orbit, then they would like to bond with other elements, and if they don't, then they don't like to bond. You can see the one on the right here is actually a beryllium. I'll double check. A beryllium element, or an atom of beryllium. And the way that you know that it's beryllium is based on the number of protons. So it's got 4 protons, just happens to have 4 neutrons too, in this case, and 4 electrons to balance out the 4 protons. And just one thing we do want to add, for the kind of chemistry that we're talking about, particularly like water-based chemistry or air-based chemistry, the number of electrons is equal to the number of protons, and that makes it an uncharged atom because it has an equal number of positive and negative charges. Elements are the building blocks of the universe. They cannot be broken down any further by chemical means. If you think about what the word element means, element is like elemental, elementary. It is the thing that's the fundamental building block. There are more than 100 known elements, and they're finding more all the time. I shouldn't say all the time, but they find them using nuclear chemistry. The ones that we observe on Earth, as far as we know, are the only ones in the universe. So if we observe hydrogen here on Earth, we know there's hydrogen everywhere else in the universe too. Zirconium is also something that you could find anywhere else in the universe as well. Now, of course, we don't know. We've never been to other places in the universe, so maybe there are other elements that we don't know about. But as far as we know, these are the only ones that exist. And they do not change. Compounds of elements can combine, combust, precipitate, but the elements themselves stay as elements. Lithium is always going to be lithium, unless you go and do nuclear chemistry on it. So as I say, there are nuclear engineers who disagree, because you could take something like uranium and do some fission to it and actually break it down into, I think, thorium or something else, a different element, but only under nuclear conditions. And the release of energy is phenomenal. So in the mid-19th century, so the 1800s, scientists started noticing a repeating pattern, a periodicity to the chemical properties of the elements that were being discovered. And that's what the periodic table means. When they say periodic, they mean that it's repeating. They're seeing these properties that started to repeat. We don't call it that anymore, but there used to be magazines called periodicals. So, or you could go to the periodical section of the library. All that means is that they tend to come out on a regular cycle. Dmitry Mendeleev is recognized as being the first to organize the elements by chemical mass. Interestingly, we don't actually organize them by chemical mass anymore. Now we organize them by the number of protons. But at that time, he organized them by atomic mass and formed groups and periods. So on the right-hand side, you can see here, I have groups that are the columns of the periodic table, and then periods are the rows of the periodic table. Elemental groups have similar properties. So names like alkali metals, alkaline earth metals, halogens, noble gases. All the noble gases, for example, are very unreactive. They tend to just want to hang out by themselves. And then it's also, like I said before, the modern periodic table is arranged by atomic number, not atomic mass, the number of protons the element has. So if you look at this periodic table, you can see that it's organized by number of protons, and the proton is really what determines what the element is. I'm sorry, the number of protons. So if it has 25 protons in it, we know it's manganese. If it has 27 protons, we know it's cobalt. But the isotopes can change. We'll talk about isotopes later. So the number of protons is set for every element. And if you change number of protons via nuclear chemistry, then the properties of that element change as well. If you're able to change nitrogen into carbon, it no longer acts like nitrogen. Just because it lost its proton, now it acts like carbon. There's a lot of information tucked away. So on the previous slide, I showed you a periodic table that just had the atomic symbol of the elements and the number of protons, the atomic number. But on a bigger scale, periodic table, you can see there's a lot more information. So for gold, on the right-hand side here, you can see that it has an atomic number of 79. It's given to us here. 79 has an atomic weight of 196.97. The common name is given there, gold, and the chemical symbol AU is also given for gold. The atomic mass, by the way, is the sum of the protons and neutrons for an element. As I said before, the mass of electrons is so much smaller, orders of magnitude smaller than a proton, that we only worry about protons and neutrons for an element. And you can see there that that adds up to an uneven number. So for gold, it's 196.97. That's because there are things called isotopes. And isotopes are chemicals that have similar properties as each other. So a heavier isotope of gold would act just like gold, except that it would have a different number of neutrons. So same number of protons, different neutrons. And as I mentioned, we're going to talk more about isotopes in a couple slides. Each group has similar properties. The different periods do not have similar properties. They're just the repetitions of the groups. But each group has similar properties, like the alkali metals like sodium and potassium are extremely reactive in their elemental state. You may have seen videos before of someone putting sodium into a lake or water of any kind, really, and sodium reacts very violently with the water in that lake, and causes almost an explosion. Halogens are also very reactive. So these things that are around us all the time, sodium and chloride, for example, like the salt that we sweat out, the salt in the water that we drink, is sodium and chloride. Because they're bonded together, they're no longer reactive. They're actually very stable. That's why we have a lot of sodium chloride in the ocean. But on their own, if you split sodium and chloride up, you get extremely vigorous reactions. Actually, in fact, I can relate that back to disinfection. We use chlorine as a disinfectant because it's so reactive. It tends to want to attack and break down the biological DNA and cell walls of bacteria and viruses. And then the last thing I wanted to say on this slide is that the groups help with bond ratios. You can see that you can think about it as each group has a similar number of valence electrons. So the halogens, for example, have usually one electron missing, so chloride and fluoride, versus the alkali earth metals, or the alkali metals like lithium and sodium usually have one electron available. So they're able to share that electron with the missing one that's missing on the halogens. And so you get things like sodium chloride, which is NaCl. It has a bond ratio of 1:1. 1 sodium per chloride, because it has one extra electron on the sodium. Calcium chloride, on the other hand, is CaCl2, 2:1 bond ratio, because calcium has 2 electrons that it can share, so it's able to hold on to two chlorides or chlorines. Isotopes of elements have different amounts of neutrons. So an isotope of hydrogen, for example, is deuterium. Deuterium has 1 neutron. So let me backtrack. Regular hydrogen has an atomic mass of 1, has an atomic number of 1 and an atomic mass of 1, which implies that it has just 1 proton and no neutrons, which is true. Deuterium, on the other hand, has an atomic mass of 2. It has 1 proton, 1 neutron. Tritium, you might have heard of, has 2 neutrons. So it actually has an atomic mass of 3. But the atomic number, because it's still hydrogen, the atomic number is still 1. It still has 1 proton. You can see the example on the right there. 1 proton, but if you add a neutron, it becomes deuterium. If you add 2 neutrons, it becomes tritium. But similar properties. It still behaves like hydrogen, mostly. Now, those things do combine. You might have heard of something called heavy water. Heavy water is something that is water that is preferentially filled with deuterium in the hydrogen. So H2O, it would be 2 deuterium atoms and 1 oxygen atom, but you still get the similar properties as water, just a different weight, different atomic weight. Many isotopes are unstable and release radiation as they decay, and so that's why we generally the ones that we see on Earth are the ones that are stable, that are not radioactive, because of course they would have already degraded, they would have already undergone fission or whatever nuclear reaction they're undergoing, and they'd be gone by now. But some are somewhat more stable, and some are being generated. So carbon-14, for example, you might have heard of radiocarbon dating, where archaeologists and anthropologists are able to determine how old materials are, organic materials, based on the ratio of carbon-14 in their to regular carbon-12 in their tissues or their organic molecules. And the reason why that works is because carbon-14 is actually generated in the atmosphere. So it's generated by bombardment of cosmic rays onto nitrogen in the atmosphere. And then as animals and plants grow, they incorporate, as plants grow, they incorporate that carbon-14 into their tissues. Then the animals eat the plants, and they also incorporate the carbon-14 into their tissues. And so, but once an animal or plant dies, then there's no more uptake of carbon-14. And so if you look at and then it starts to degrade. It degrades back into nitrogen. So you can see here in this sketch here, we have 6 protons and 8 neutrons in carbon-14. That's up to a total mass of 14. It undergoes a nuclear reaction where an electron is shot off and forms into 7 and loses essentially gains another proton. So it goes from being 6 protons and 8 neutrons to 7 protons and 7 neutrons. And that, because it has 7 protons, is now nitrogen. So it changes the actual element because of it's a radioactive reaction. Does that make sense? So once the animal dies, it no longer is taking up fresh carbon-14. The carbon-14 that's stuck in the tissues slowly converts over back to nitrogen. And so you can look at the ratio of carbon-14 to carbon-12 in an animal tissue and find out how old it was, up to about 5,000 years. There's a lot of different ways to use the periodic table. You can use it to find data. So if you're trying to figure out what the density of something is or what the atomic number is, you just go to your periodic table and it will tell you. You can find out the chemical symbol, the atomic number. So all this different information is there. And then even you can figure out what the bonding should be by relating elements to each other by group. So you can, like I said, estimate the bonding patterns. We talked about that briefly before. But something like sodium chloride, it's a 1-to-1 bonding ratio. Calcium oxide, oxygen has a vacancy for 2 electrons. Calcium has 2 spare electrons. So you get about 1-to-1 ratio there too. Something like calcium chloride, again, we said this is a 2-to-1 ratio. And then something like sulfur, H2S, it has a 2-to-1 ratio as well. I've never heard of rubidium bromide, but I can tell by looking at the table that rubidium bromide would have a 1-to-1 bond ratio because rubidium is in group 1, bromide is in the halogen group. Okay, so we have 2 example problems we're going to work. The first one is we need to measure out 0.05 moles of calcium hydroxide using a scale. What mass should you provide? Because of course, scales don't measure in terms of moles because every element has a different molar mass, and a scale really only measures the attraction of an object to the Earth's center. So really, it actually measures weight, but we can convert that to mass for Earth-based scales. But the first thing I'm going to do is figure out what is our atomic weight of calcium hydroxide. So I can go back to my table, and I'm not going to worry too much about the round numbers because this is just an example. But if I look at calcium has an atomic weight of about 40. So 1 calcium, oxygen has an atomic weight of 16, and hydrogen has an atomic weight of 1. So we add that together and we get 57 grams per mole. Okay. 57 grams per mole is the atomic weight or atomic mass of calcium hydroxide by adding the different atomic masses of the different elements in it. Now we can figure out how many moles that is by multiplying times 0.005. Sorry, 0.05. We want 0.05 moles of calcium hydroxide. We know it's 57 grams per mole of calcium hydroxide. And so we just multiply that out and we get that we need 2.85 grams of calcium hydroxide to have 0.05 moles. And then, of course, if we're trying to make a solution, we can add that to a set amount of water and get a molar concentration too. Next example, we have a beaker with some calcium carbonate precipitate. We originally added 5.5 grams of calcium to a solution with an excess of carbonate. How much carbonate was precipitated? This one's a little more complicated, but we can actually use a similar approach to unit conversions to solve it. So if we started with 5.5 grams of calcium, so again, what we're doing here is we have a solution that was saturated with carbonate. We added some calcium to it, and we want to know how much of the carbonate will precipitate as calcium carbonate. We know that calcium is 40 grams per mole. Calcium is 40 grams per mole. So now we know how many moles calcium we added. We can cross out grams. We know that there is 1 mole of carbonate because calcium carbonate forms. So it's a 1-to-1 ratio. So we know it's 1 mole calcium per mole of carbonate. Okay. And we know that a mole of carbonate weighs 60 grams. 12 is carbon. 16 for oxygen, and we're left with 60 grams per mole for carbonate. Okay, so we know it's a mole of carbonate weighs 60 grams. And we can cancel out moles of calcium, moles of carbonate, and we're left with grams. And that's the unit that we're looking for. So we double check, make sure that we're looking for grams, because if I might have asked for milligrams instead, and then you would just do one more step. And if we run through those numbers, we take 5.5 times 60 divided by 40. So we just multiply the numbers together across the top and divide by the numbers across the bottom. And we're left with 8.25 grams of carbonate precipitated from our solution. And here are your practice problems. So you can work these on your own. Which of these is not an actual compound? You can use the periodic table to look at the bond ratios that you would expect to see, and then compare and contrast to see which one of these is not correct. And then a similar approach, how many chloride atoms would you expect to bond to each of those elements? I hope this has been helpful for you, and I know it will apply to your future classes.